All right, so this was the lesson that we were going to do Friday. So we're going to do it today instead. So we'll just kind of be a little behind, but it'll be okay. We can probably play catch up. So today we're going to look at whose derivative is it anyway. So we've already looked at some antiderivative rules, so the power rule. But today we're going to kind of explore more integrals just as functions themselves. So we'll learn some key features of their graphs and their equations and kind of what's special about them. All right, so take a second and see if you can answer these first 5 questions. Pause the video, work through it yourself, and see what kind of answers you can come up with. Okay, so 2 polynomials are shown. Which one is the original function and which one is the derivative? So the cubic function is going to be the original function. And the quadratic will be the derivative. Okay, so the cubic function then is called my antiderivative. And a lot of times they do the antiderivative as a capital F of x. So capital F of x like this. And then they label the derivative as a lowercase f of x. So a lot of times when they talk about it, when we set it up, that's the notation. All right, so what features of the graph show this relationship? So I'm just going to tell you some things that people have said that maybe that you can notice. So f of x has extremas. When the derivative, and I'm just going to write it like this so that we know the difference right now. When the derivative has an x-intercept. Right? So I've got extremas where I've got x-intercepts right there. All right. F of x is increasing where the derivative is greater than 0. So where it is above the x-axis. And then what happens right here? So what's happening here? It's decreasing, and then the derivative is below the x-axis. Alrighty. So how can I find an equation of the derivative? So look at this derivative. How can I find an equation of this derivative? Okay, remember our vertex form. So vertex form is a times x minus h, all of that squared, plus your k. So your vertex is 1, -3. So this will be a negative 1 squared minus a 3. But now I've got to figure out what my A is. The other way that I could put it is just by my x-intercepts, right? So if you thought about it that way, you could put it in that form. You still have to figure out what A is. So it would be x minus h. That's not good. Hold on. Let's not call that h. Probably need to move that. So, I don't know, x minus p, and then x minus q. So either one of these forms is fine. All right, so now I need to figure out what A is. So it is increasing by 3. So see that? So from the vertex, so from a normal parabola is here, right? So it's just kind of by a factor of 1 right there, but this one is actually by a factor of 3. So there's going to be a 3 on that outside. All right, so my derivative, I'll write it like that. It's going to be 3 times x minus 1 squared minus the 3. All right, so I want to find a general solution. So what would help me just to go ahead and multiply this out. So I could get a general solution. So that's what, x squared minus 2x plus 1. So I'm gonna put a square right there, I'm sorry. All right, so if I multiply my 3, that 3 is going to cancel out. So I'm just going to be left with 3x squared minus a 6x. So now this is going to be a little bit better to find a general solution. Okay, so let's set up a integral like we did on the circuit to do this. So it will look like this. I'll have this, and remember, there was something special I had to have attached to all of this. So I have to have my differential. This variable has to match, remember, what's inside there. Okay. So now, can I integrate this? Okay. So it's going to be what? 3x cubed over 3. And this is going to be m minus a 6x squared over 2, and then plus a c. So this will end up being x cubed minus a 3x squared. And then remember, you always have to have that plus a c. Okay, so we talked about general solutions are solutions that just kind of represent any of the functions. So any that c can represent any value there. So I could draw another solution. So all it would have to do is just be something that looks similar. So I don't know, let's draw one like this. So like to there, so it's increasing. It's got a peak there. Turn around and say it's got a peak there. And then increase. So this one would actually also match. It's terrible drawing, but this would also be another example. Like any of them, you could have drawn it anywhere if it would have looked like that. So I mean, it could have gone way up here like this. I mean, something like that. So just had to represent the peaks and the valleys. All right, so how do I find a particular solution that goes through that 0.04? So does actually represent this one. So a particular solution is different than a general solution. Particular solution is me solving for that c. So now I need to find that c. So what would I do to find that c? I could plug in 0 for my x, and right. So what's going to give me that 4? And so in this case, my c is going to be equal to 4. So my particular solution, so the actual function, is going to be x cubed minus 3x squared plus a 4. Good. All right, so antiderivatives and initial value problems. So initial value problems are when you find a particular solution. So let's first set up an integration. So remember, I labeled them little f of x and big F of x. Let's label the parts here. So I've got my integral sign. This is my derivative. This is my differential. This is my antiderivative, my original function. And this is my constant of integration. All right, so a particular solution, I guess we'll label this one, particular solution is an initial value problem. So this is when you solve for c. All right, so we've talked a little bit about some rules, but here let's kind of do some antiderivative rules. That would help. All right, so we did our power rule. So if n here does not equal a -1, because I have a special case if it's equal to a -1, then it's going to be, I'm going to add to my exponent, and then I'm going to divide by that exponent. Okay. If it is equal to a -1, that means that it is just 1 over x, and whose derivative is 1 over x. And that's a natural log of x. But we have to have it in absolute values because there is like no minus sign or anything. So just think about that. We've got to have positive. All right, so let's go up here and do we wrote these out, I think, the other day, but let's just write them so we all have them. Whose derivative is sine of x? It's going to be negative cosine. Whose derivative is cosine? Not a negative, sorry. So that's just sine. All right, whose derivative is e to the x? That's just going to be e to the x. And then this one, whose derivative is a to the x. So this one's going to be a little different. So Think about this one. This one's e to the x, really divided by ln of e. And when you divide by that ln of e, that is just divided by 1. So this rule right here that I'm about to show you is really no different, but it's just I have something in the bottom. So whose derivative is a to the x, so that's going to be a to the x over natural log of a, and then plus a c. Okay. All right, there's a lot more of these, but these are the ones that we're going to look at right now. All right, so take a little bit of time and try to work this back, pause, and then come back and check your answers. All right, so how did you do? So whose derivative is 7dx, so 7x plus a c. Whose derivative is 3x squared minus 4, and that is x cubed minus a 4x plus a c. Always remember you can take the derivative of it, and if you don't get back what you started with, then we've got a problem. Whose derivative is 4e to the x, so that's going to be 4e to the x. D, you would need to simplify first, so whose derivative is x cubed plus 5 over x, so separate that out and simplify. So it's going to be x cubed over 3 plus 5 ln of x plus a c. Whose derivative is cosecant squared, so it's going to be a negative cotangent. This one's a little bit kind of tricky because this one all we know is in terms of sine and cosine right now. So I would just separate this and take sine. Since you've got cosine squared, if it was flip-flop, they flip-flopped, but sine over a cosine, and then times 1 over a cosine. Sine over a cosine is tangent, 1 over a cosine is secant, and then whose derivative is tangent x secant x. And that, of course, is secant x. Secant of x. All right, whose derivative is 7 to the x. So here we go. And then whose derivative here, this one's a little tricky because we do have to divide by this, because if I were to just integrate it or take the derivative of this, remember the derivative of this, I multiply, it's a chain rule happening, so I would multiply by the derivative of the exponent. So in this case, I need to divide by it. Okay. All right, so if I wanted to find f of x here, knowing that the second derivative is given to me, and I have a condition where I know my first derivative, like points on the first derivative, and I know points on my function. So first things first, I need to find the first derivative, so whose derivative is x cubed minus 2x plus a 1. All right. And then plug in, so plug in this condition here, 0 and 1, and so you're going to get that your c is going to be equal to 1. And then whose derivative now is this, so using that rule here, so it'll be x to the 5th over 20 minus x cubed over 3 plus x squared over 2 plus an x plus a c. All right, so this is a kind of a FRQ here, what we would do with the free response. So we've given the acceleration. So remember, the acceleration is the derivative of the velocity function, and the velocity is the derivative of the position function. So that's kind of something to remember. So we can apply that to acceleration. So if I wanted to find the velocity function, I would say whose derivative gave me this. So I would integrate 2t minus 10. And I know this initial value here, so I can find a particular solution. So I know this initial value, so I can find a particular solution. And then same thing with finding the position. I'm going to integrate the velocity function. And then if I figure out when the particle is going to move right, left, or stop, then we're going to set the velocity equal to 0. If I set the velocity equal to 0, that means that these are the points where it's going to stop. Okay, so it's not in motion. So then I've got to figure out to the left of it, between it, and then to the right of 6 what's happening. So you'll plug values here inside and see what happens to your function. All right, let me know if you have any questions, and hopefully I will see y'all on Friday.